Hey guys, so in today's lecture, we are going to discuss a new chapter that is wind energy. So, this is also a renewable energy which we are going to discuss. So, in today's chapter, we are going to discuss two topics, that is energy available from the wind and effects of wind speed and rotor diameter on wind power. So let's see first what are the topics which we are going to get familiar with in this chapter according to the syllabus. So that is energy available from the wind, basics of lift and drag, then basics of wind energy conversion system, effect of density, angle of attack, and wind speed. Then different types of windmill rotors like horizontal, vertical, axis rotors. Then drag, lift, torque, and power coefficients. Tip speed ratio, solidity of turbine. Then various cause, wind energy potential and site selection, and basics of wind farm. So these are the topics which we are going to discuss. So in today's lecture we will start with energy available from the wind. Before starting that, let's let me give a brief introduction of wind energy. That is, as we know that wind is essentially air in motion which carries with it kinetic energy. The amount of energy contained in wind at any given instant is proportional to the wind speed at that instant. So, which means that how much energy does the wind has, it depends on how much speed it is having. So, it is therefore its energy is totally kinetic energy. So the temperature of the wind also influences the energy content of the wind, but it is not important in the context of wind based energy production system. So temperature also plays an important role, but we are not interested in temperature effects because in producing the energy from the wind. So wind results primarily by unequal heating of Earth's surface by the sun. About 2% of the total solar flux that reaches the Earth's surface is transferred into the wind energy. So, solar energy meets clouds, uneven surfaces, mountains while reaching the earth. This unequal heating causes temperature, density, and pressure differences on the earth's surface that are responsible for local wind formation. During daytime, the air over the land mass heats up faster than air over the ocean. Hot air expands and rises while cool air from the ocean rushes to fill the space, creating local winds at night. The process is reversed as the air cools more rapidly over land than water over offshore land, causing breeze. On the global scale, the primary force for global winds is developed due to differential heating of the earth at equatorial and polar regions. Due to different heating at different places, the the global winds are caused. In the tropical regions, there is a net gain of heat due to solar radiation, whereas in the polar regions there is net loss of heat, and this means that Earth's atmosphere has to circulate to transfer heat from tropics towards the poles. Also, spinning of the Earth about its axis produces a Coriolis force which is responsible for deviation of air currents towards the west. The global potential in winds for large scale grid connected power generation has been estimated as 9,000 trillion watt per year. The idea of harnessing winds is not new, as we know that it was one of the first natural energy sources to be used by mankind. There are indication that windmills were used in Babylon and China around 2000 and 1700 BC to pump water and grind grains. Egyptians used wind power to sail ships in the Nile some 5000 years ago. The interest in wind energy has renewed after the oil crisis of 1973. Most modern large scale wind energy systems have been built after 1980s using modern engineering designs, materials, and incorporating microelectronics monitoring and control. Several demonstrations and commercial plants of different sizes, from few kilowatt to few megawatt, are in operation in different parts of the world. The following main factors that have led to the accelerated development of wind power are: first, the availability of high strength fiber composites for constructing large low cost ro- rotor blades, variable speed operation of electrical generators to capture maximum energy, falling prices of power electronics, improved plant operation, pushing the availability up to 95%, accumulated field experience, improving the capacity factor, economy of the scale as the turbine and plants getting larger in size. So this were the main factors that has accelerated the wind power generation in the world. So now we will see what is the power that wind has. So we will see by mathematically. So as we know that the power the wind has is directly proportional to its velocity. So that power that wind has is kinetic energy. So windmill and turbine converts the kinetic energy of the wind into mechanical energy. The total power of wind stream is equal to the rate of kinetic energy. So kinetic energy, as we know by the formula, that is 1 half mv square, where is mass m is mass, while uh, v is velocity v is velocity, and the amount of air passing in unit time, that is how much cubic air, how much volume of air per second is passed. If we want to calculate that, then we'll we get that is amount of air passing in unit time through an area a through an area a, and having velocity v, so that will be equal to a into v, that is area into velocity. Now the mass flow rate of air that is m dot, will be equal to rho a v. So it is density. Rho is density of the air, then area through which air is passing, and v, velocity of the air. So substituting the value of mass in kinetic energy's formula, we will get that kinetic energy will be equal to 1 half into rho a v into v square. So after opening the brackets, we will get that kinetic energy is equal to 1 half rho a v cube. Now this kinetic energy is called power in the wind. So we will denote it as P total, that is total power of the wind. It is 1 half rho A V cube. So all this power cannot be extracted because for this wind velocity would have to be reduced to zero, which means that the windmill could accumulate static air around it, which would prevent the windmill operation. So it is clear that the total wind power varies as cube of the wind velocity, directly proportional to wind density and directly proportional to area of the stream. So the wind turbine produces maximum power at high wind velocity. So wind velocities below 5 meter per second and above 25 meter per second are not suitable for wind turbine. At lower speed, very large turbine rotor is required, and at higher speed, the stresses on the turbine blade and shaft are very high. So from equation, we wind power is proportional to the intercept area. So wind power P is proportional to the intercept area, that is A. Thus wind turbine with large swept area has higher available power. Normally the area is circular with diameter d, therefore area is equal to pi by 4 d square. Area is equal to pi by 4 d square. Therefore the total power PT after substituting the value of area, that is pi by 4 d square, will be equal to pi by 8 rho d square v cube. So from this equation it is clear that power P is directly proportional to the square of the diameter of the swept area. P is proportional to d square. The combined effects of wind speed and rotor diameter variation is shown in next slide. So and P is directly proportional to velocity q. So let's plot the graph. So here from the equation, we have plotted the graph for effects of wind speed in meter per second and rotor diameter in meter on wind power. It is megawatt. So on the x-axis we have wind speed, and on the y-axis we have wind power. So as we know that wind power is proportional to the cube of wind speed, that is cube of the wind speed. So for any rotor diameter, so as wind speed is increasing, the power is increasing cubic way, in the form of cubic. And similarly, as power is increasing, as we know that power is proportional to the square of diameter. So as power is increasing, the the sorry so as we know that as rotor diameter is increasing, as we are increasing the rotor diameter, so as power is proportional to the square of rotor diameter, so the power is increasing, or power is also increasing in the square way, in the square way. That is, if we are increasing the rotor diameter from 20 to 40, the power is increased square in much more times. So this is the effect of wind speed and rotor diameter on wind power. Now the next uh, the next topic is wind. The next topic is power coefficient. So what is power coefficient? So the fraction of the free flow wind power that can be extracted by a wind turbine or rotor is called power coefficient. So mathematically it is shown that the power of the wind turbine rotor divided by power available in the wind. What does it mean? That how much power we can extract from the wind, that is power coefficient. So the power that can be extracted by a wind turbine rotor. So the maximum theoretical power coefficient is equal to 0.593. The maximum is around near to 59.3 percentage. So this value cannot be exceeded by a rotor in flow wind stream, as an ideal rotor with propeller type blades of power aerodynamic design would have power coefficient approaching 0.59. So as an ideal rotor with propeller type blades of such aerodynamic design would have 0.59, but such a rotor would not be strong enough to withstand the stresses to which it is subjected when rotating at a high rate in high speed wind stream. For best practical rotors, the power coefficient is about 0.4 to 0.45, so that rotors cannot be used more than 40 to 45% of available power. So we can get a maximum efficiency of near to 40%. So we cannot extract 100% of the wind power. So this is the main topic, how much energy is available in the wind and how much we can extract it from the wind. So in next lecture we will see how we can extract the power from the wind. So in this lecture we have seen how much what power does wind has and how much we can extract. Next lecture we will see how to extract power from the wind. Okay, so and we will see some derivations and mathematical equations also, and we will also see what are all are the forces on the blades and the end thrust on the turbines. So, that too are very important topics, so which we'll discuss in the next lecture. Okay, so thank you very much.